Welcome everybody, you're watching 𝗦𝗶𝗺𝗽𝗲𝗀 Data Science. Today, I would like to go over the basics of linear regression, solving with the least squares method. Feel free to reach out to me on socials. Let's get started. Linear regression is a great tool to build upon your data analysis skills. But why is it important? In general, we are interested in obtaining the best fit line for the data that we have so that we can make the best prediction possible. Today, we will work out an example to see how this works, see calculations, as well as explain each step along the way for a better understanding. This video will help anyone learning or rusty with the topic. I will solve this using least squares. Remember, linear regression is used to make predictions. These predictions are based on some given x value, and we are trying to find a corresponding y. Remember your basic equation of a line? This is the same thing, but notated differently. Before we get started, I would like to mention something important in terms of notation and understanding. When we reference a data set, typically we are referring to a sample, not the population for our predictions. This is because we usually do not have enough information about a population that we were trying to make a prediction from. This means that while we have data, the estimations are based on these data and modeling the behavior of a possible population. Instead of the standard y equals mx plus b, you will see f hat equals ax plus b. F hat represents an estimation or a prediction from a data set. This distinction is an estimation of y for a given value of x. A is our slope, b the intercept, and x or your independent variable. Something you will hear often and may cause confusion at first are further terminology. Your y variable is considered the response variable, responding to what the x variable is doing. We are trying to explain y based on the actions of x. This is the variable we are predicting, by the way. Next, we have x variable because it is used to explain or predict the value of y. Your x value will be your independent variable, as I said before. With the data plotted in a scatter plot, we can investigate to check for outliers and see if the data makes sense for a general observation. We are interested in creating predictions based on values of x and also finding the best fit line for these data. If you remember from algebra, we have an infinite amount of lines we can generate, but for our purposes, we are interested in the best fit line. Here's a few lines, but which is really the best of any of these? And how can we find the best fit line and understand what's going on? For us to make predictions, we need to understand the error within our data and minimize this. An important thing to mention also are outliers. These will need to be accounted for before we do any processing. This will need to be accounted for because any further interpretation or analysis will be skewed. The error I'm referring to is called residual error. The vertical black line is the error between the observed data point in blue and the predicted value, which lies on the best fit line. We are trying to minimize the distance between each point and the line. When this occurs for all points, we have the best fit line to make our predictions. Let me distinguish this for you. The observed data point corresponds to the actual data point from our data. The predicted value corresponds to the theoretical value of y, predicted, which lies on the line. Notice the notation of y hat. Check the visual representation from this plot where the orange dots are the predicted values, the blue are the actual data points, and the vertical black lines are the residual errors that are inherent within our data. This variability is what we are minimizing. I want to reiterate this so it sticks with you. Black lines are the residual error that is inherent within our data. This variability is what we are trying to minimize. I'm only reiterating this so it sticks. How are we going to minimize our error, and where do we even start? Considering that we have data points only and no suggestion of a formula, we need to work backwards. I decided to use least squares method, which will help us see what is going on and understand this a bit better. Starting from our formula of y hat equals b plus ax, we need to find the intercept and the slope. I will do this in 3 steps. First, find the Pearson coefficient, then the slope, and then the intercept. Remember, our goal is to minimize error within the line in order to make predictions. First step, we will calculate the Pearson's coefficient so that we can find the slope afterward. The Pearson coefficient is used to find the relationship between two variables that are linear. There are a few things with this value which are interesting. The closer you are to 0, the weaker the relationship there is between the variables, meaning that they are not correlated. The actual sign, positive or negative, only refers to the direction of the slope, not the amount of correlation. At this point, if you have outliers in your data, data, you need to get rid of them because this will drastically affect your calculations and affect the results. There's something cool that I want to mention from the relationship you see with the Pearson coefficient. The numerator for the x and the y relates to something called the deviation. In the denominator, you'll see the sum of squares for the x and the y. It's related to the variation. And because of this, you could find variance and standard deviation from it. If you see the bar on the top of x and the y, that's standing for the mean, if you're unfamiliar. Another interesting point about the numerator of the Pearson coefficient would be the product of xy deviations. It's calculating the variability between two variables. This can be related to the covariance with a minor manipulation, by the way. This is just a side note. In order for us to find the Pearson coefficient, we need to find the mean of x and y, which is simply the sum of x values divided by the number of observations. Repeat this for y as well. We can create a table with 7 columns to make this easier for calculations and avoid making mistakes or forgetting something. The first 2 columns are the x and y values that are observed from your data set. Next, we will have the deviation of x as well as for y in separate columns, the product of the deviations of x and y. The last 2 columns will be the sum of squares for x and y. Before we move forward, we need to gather the mean for x as well as y observations. Look at the bottom and you'll see that we have the sum of all the values of x, and then we need to get n, which represents the number of observations observed. In our case, it's 11. So we do the sum of x values divided by 11, which equals almost 600,000. It's 592,000 and change. After we do that for x as well as y, we can look at column 3. This is our deviations. We will take the observation of x, subtract it from the mean, and do that for each entry. We'll start with the first entry, which is 278,000. Then we will subtract the mean value, which is 592,755, and we end up with a negative 314,755. That's the first value in the deviation of x. And you do that for each of the 11 entries. And you do the same thing for y. After you're done with y, now we are working with the 5th column out of 7. It's the product of xy deviations. So from the last step where we did the x deviation and the y deviation, we store those values in the table. And now we could go row-wise and multiply each entry to get the product of deviations. This is the variability between two variables. If rewritten, we could relate this to covariance, like I said before. If you look below, you'll notice that we need to calculate the sum, which will be needed later, which is the product of the x as well as y deviations. From there, we calculate the x and y sum of squares. The good thing about this, we can go to the first column you see on the left, which is the negative 314,755. This is the x deviation, and we could just square this, and that will give us our first row of the x sum of squares. And when you do this, we'll calculate it for each row, and at the end, we need to sum all of the rows. Then we repeat this for the y, and if you notice, we'll have the sum of each of those at the bottom, which will be used for our calculations. Finally, we're at the point of putting everything together to calculate the Pearson coefficient. The numerator is the product of x and y deviations. We need to sum everything together and put it in a numerator. You see this red box, and at the very bottom is the final tally. We'll have to go over to the right 1 column, which is the x sum of squares, which is the first value in the denominator, sum all of those values, same thing for the y, and then we have to take the square root of everything, which is very important. Pay attention to that. Don't forget that step. And we end up with the 0.913. And yeah, you should pay attention to your significant figures. Usually this is 2 digits, but I'm taking it out to 3. Now that we calculated the Pearson coefficient, which is 0.913, you can look at it like this. It's the strength between 2 linear variables. The closer you are to 1, the stronger the relationship. But I would not say that this is a correlation. If we were to recap real quick, we could see something. You've heard the term R squared. Well, if you take that Pearson coefficient and you square it, you'll end up with 0.834. This would equate to 83.4% of the variance in response variable can be explained by the explanatory variable x. The remaining variance is unexplained due to other factors not included in the formula. Interpretations can can vary depending on your data and the context. In some situations, we can use smaller values of R² if we know the smaller value is acceptable. Keep this in mind as prior knowledge. After we found the Pearson coefficient, we will find the slope, which would be denoted as B in this case, which equals R, standing for the Pearson coefficient, times the standard deviation of Y divided by the standard deviation of X. We will write the standard deviation in this case as the sum of squares of X divided by the number of observations of X minus 1, and take the square root of that. The n minus 1 is because we're dealing with a sample, and because of that, we're doing estimations. If this was a population, it would be n. That's the distinction if anyone's curious. And you'll do the same thing for y. The great thing is we have our table, so we can go to the table portion, which were the last two columns that we had, and we have the summation of each of these, which makes everything better. We just plug and play. So you just take the sum of squares of x, we have that calculated, and then we have 11 observations or 11 rows minus 1, and do the square root, and we found the slope. Now we just need to plug in the values for the x and y sum of squares, and then the number of observations, calculate the standard deviation, and then we'll do the Pearson's coefficient multiplied by y standard deviation divided by x standard deviation. We end up with the slope equaling 0.003. But there's an issue here because I rounded prematurely. Now I should have left it at 0.0027 or 0.0273 as a distinction. After that, we move on to we're getting closer to the end. We'll start with the formula of hat equals a plus bx, and we will rearrange to find a, which will be our y-intercept. Considering we have the slope, the mean of x and y, we will instead utilize x mean in place of x and y mean in place of y hat. Since we're dealing with an estimation of the sample and not the population, an important message is this: since we know that the mean values lie within the line, we can use those to plug in for the x and the f hat. Since we have everything rearranged solving for a, I want to try two things. If you notice, on top we will have 0.003, and on the bottom it's 0.0273, the unrounded value. After plugging in the mean of y, which is 2730, subtracted from 0.003 multiplied by 592754, which should be rounded to 55 instead. The top says 951, which should go to rounded to 952, and the bottom is 1130. But which one really is correct? Because you see the swing in values. Well, because of the rounding, that's what causes the discrepancy. And I should have taken instead the approach of thinking like this. The x and y values from our original data set were whole numbers. When I got the Pearson coefficient, that one I should not have rounded yet and waited till the end. Therefore, if we look, I should keep the 0.0027 multiplied by the x. Where do we go from here? We have the formula for this particular line based on our data. F hat equals 1130 plus 0.0027x. If we want to try an example, we can plug in x equals 545,000, which represents dollars, and we output F hat, or the predicted y, equals 2618, representing the amount of square foot we would have for this property. Looking at the plot that we have here, the green lines will show where it lies on the line, and the black dot signifies where it lies on our line. The orange dots are predicted values from the corresponding blue dots, which are the observed data. If we go on to the next plot to simplify this, we can go back to what we mentioned before. In x and y observed value is the corresponding data points that we got from the data set. The vertical black line is the amount of error we have with respect to the line, which is our best fit line. The point that lies on the line is the predicted value of y with respect to an actual value of x. Let's step back a little bit from our last example and reiterate again. Along this best fit line, all the values that lie in it are the predicted values that are placed in orange with respect to the blue values observed in our data set. The predicted value is a y given a known x. If we had a known xy pair, which was 278,000, and we know that the square feet is 1900, what predicted square feet can we get? Plugging that in as our x, we end up with a predicted y, or f of x hat, is 1800, saying that if we knew what x was in dollars, we can predict 1800 square feet, even though in our data set it was actually 1900. Let's do a quick little example from the actual data. If you look on the right-hand side, an actual data point of $533,200 had a observed 3,000 square feet. If you plug that into our formula to find the predicted y, or f hat, we end up with 2570. The distance from the observed to the line where the predicted value is error, residual error. In the next video, I'm going to go over different types of error for us to have some clarification and see how this works. That'll be the end of this video. If you thought it was useful or informative, consider hitting that like button below. If you'd like to see similar content, consider subscribing. Those who may want to support the channel, I have Buy Me a Coffee, Super Thanks, channel memberships, and Patreon. Thanks again, and like I said, next video I will discuss different types of errors and round off this linear regression model. See you in the next video. Bye.
Run free.